So welcome everyone to our STAMPS webinar series. We are very fortunate to have Dr. Derek Bingham here today. So Derek is a professor of statistics and actuarial science at Simon Fraser University. Derek received his PhD in statistics at SFU, and after graduating, he started as an assistant professor at the Department of Statistics at the University of Michigan. In 2003, he joined the SFU Department of Statistics as the Canada Research Chair in Industrial Statistics. And Derek's current research is in developing statistical methods for combining physical observations with large-scale computer simulators. And his research and methods are, in the true spirit of STAMPS, motivated by real-world applications. And Derek is actively collaborating with scientists at US National Labs and the US Department of Energy. So today he will talk about computer model emulation and uncertainty quantification using a deep Gaussian process. So Derek, please.
Right. So thank you. Thanks for the invitation, and thanks for the wonderful introduction. So before I get going, I'm going to say a few things. This work started, as I was mentioning to Ed before, that this work started with a collaboration at the Newton Institute with Ilya Mandel, who's an astronomer, and Danny Williamson, who was one of the program organizers on the program on uncertainty quantification. But really, the hard work was done by Fraser, who is a PhD, was moving on as a postdoc, was a PhD student in the Department of Statistics and Actuarial Science here at SFU. And I've chosen this talk, so I will call myself a methodologist. I tend to like working on applications, and we'll call it big science, and seeing what sort of methodology we can create to help solve their problems, and then start working out the foundations. So I often will say that the solution we come up with, because the scientists are working on a different time scale, the solution we have is the now solution, so not obviously wrong, and then we try to work out all the details, the finer details, and study the properties of methods. So that's kind of the strategy that I take in my research. And I've chosen this particular talk amongst the sort of projects that I've worked on because there is actually a large CMU component in this work. So I'll try to highlight that. But for those of you who are at CMU, or in particular, if there's any graduate students, you'll see some of the impact of your predecessors and also the faculty. Let's see if I can. It's working. Here we are. Mandatory outline slide. So I'm going to talk about our application. I'll talk about Gaussian processes, and then really talk about deep Gaussian processes and try to bring it back to the application, which has to do with this COMPASS computer model. And I'll try to recap. And if I have time, I'll talk about kind of the next steps that we're taking. All right. So our application. So here we're interested in emulating the behavior of merging binary black holes. So you can think of these as you've got two black holes in a system, and they're orbiting around one another. And when they merge, energy is released and in the form of gravitational waves. So those of you who are familiar with the LIGO study, that's one of the sources of gravitational waves. And in particular, as they spin closer and the rotational frequency increases, you get as they collide, if you will, or they merge, you get, we can observe this, or we hear this in the form of something called a chirp. And what we're going to be specifically interested in is something called the chirp mass. So the mass that's expelled as the binary black holes merge. You can think of it like that. So how does this work? So we want to construct an emulator in fact, this is of a population synthesis code. So interest lies in the characteristics of the binary black hole merger. So that's really what the physicists or the astronomers are interested in. So usually, you begin with an initial binary system, so called the initial stellar binary. So there's two stars, if you will, and on the top left, and the primary star, the larger of the two, starts, it goes through its evolution and towards being a black hole. And as it does that, it expels. There's a mass that is expelled, and as that mass creates this envelope around it, it ends up transferring some of that to the secondary star. So as the primary loses that envelope, and the secondary star absorbs some of that mass, the primary collapses into a black hole, and then the secondary star, which is now pretty big, does its thing, and it evolves also into a black hole. And there's a mass transfer from the initial smaller star onto the black hole. And then they form this common envelope, which you see in step F. And eventually, as it becomes a black hole, there is a ejection of that common envelope. And as it collapses into a black hole, eventually, over time, we have these two black holes, and they're rotating around one another, and eventually they merge. Okay, and as I mentioned, the chirp, you can see it here, and you have the sound is the rotational frequency, like that. And as they merge, you get that whoop, and we'll call that the chirp. And when that happens, mass is expelled. All right, so you could, oops, I'll do this again. So on the bottom right, you see the two black holes merging, and you got one of them spinning around one of the other one. Eventually they merge, and that's where you get that chirp. And again, the gravitational waves is what from that is one of the things that LIGO has detected. Okay, so what do we have? We have a computational model. So this is the compass model, and the inputs to the model have to do with the initial conditions of the binary system. So you've got the mass of the larger, which we'll call the primary, and then of course the secondary star, the smaller of the two. And you also have the initial orbital separation, you've got population parameters and so on. So there's a number of parameters that describe the initial state of the system. And the output, well, there's a lot of outputs. We're going to focus on the chirp mass of the formed binary. So the short-term goal was to emulate the chirp mass, and the long-term goal is to use the observations of from LIGO and other studies to constrain or calibrate the distribution of population parameters that govern binary black hole formation. Okay, so the compass model is fast, but not fast enough, if you will. It's not instant, and in the sense, it's also not readily, at the time when I wrote this, it's not readily available. It certainly is more readily available than it was when we first started this. The Ilios team has released code for their model. We'd like to exercise the code potentially billions of times. And okay, so what has actually happened is that the astronomers have created a series of code evaluations, in fact, 2 million of them roughly, for us to create a model of their model, so an emulator of their computational model, which will be faster and more readily available. So COMPASS is a deterministic model in the sense that if you plug in the initial conditions and you get a chirp mass, you plug in the same initial conditions and you'll get the same chirp mass out. One of the challenges, though, is that the set of inputs does not always result in a binary black hole system, and you don't get formation, and therefore you have no chirp mass. And so there are going to be regions of the input space where there's activity, and there's going to be regions of the input space. So for instance, if the mass of the two initial stars, the primary and the secondary star, are too small, they're not going to form black holes. And if they don't form black holes, then you can't observe a binary black hole merger. Okay, so that makes it a bit more challenging. So there's going to be regions of input space that have that are active in the sense that we observe a chirp mass, and others where we will not. Okay, so what are our challenges? The astronomers wanted a fast model of the model of their simulation model, which we'll call which we call conventionally in this area called an emulator. We have deterministic simulations, and we have a lot of them. So as I'm going to say in a couple of slides, typically Gaussian, there's reasons for doing this, but Gaussian process models are often used to emulate deterministic computational models. And there has been previous work on emulators with large simulation suites. So there's some work done by Carrie Kaufman, who is a CMU grad, and she did some work with me way back in 2011. But there's been other work on creating emulators for large simulation suites. Another challenge, as I said, was that that many of the simulation runs that we have, no output is observed, and we're going to code that as having a zero chirp mass. Okay, so next, Gaussian processes. So Gaussian processes are often used to emulate computational models or deterministic computer models as a function of the inputs. So suppose we have M model evaluations or simulations with a d-dimensional input. We have a design matrix X. So X1, for instance, is a d-dimensional input. X2 is a column vector. X2 similarly through XM. and we have scalar outputs. Of course, we don't necessarily have to have scalar outputs. We have multivariate outputs or functional outputs and so on. For this talk, we're going to look at scalar outputs. Okay, so what we do in order to model or emulate the computational model is to view the code, the response surface that's coming from the simulator as a single realization of a Gaussian process. So we can write it like this. So I've got a constant mean plus a GP. So the formulation we have a zero mean GP with a variance sigma squared, constant variance, and the correlation between observations at inputs x and x prime are described by this product squared exponential. All right, so what you really want to see here is that as the inputs, or the x's, if you will, move away from one another, the correlation among the observations decreases, right? That decreases exponentially. If you notice here, we have this length scale parameter phi, which is phi, which is allows us to look at the correlation as we move along any of the input coordinate axes. So we're not assuming typically we don't assume an isotropic covariance. And that kind of makes sense in the computer experiment world, where the inputs can be things like mass of a star and orbital separation, which really don't live on the same scale. So for our M observations, we have a covariance matrix, which sigma squared R, so R is our correlation matrix. Correlation matrix, and we have our vectors, the vectors of responses will follow a multivariate normal with a constant mean and this covariance matrix C. All right, so Gaussian processes are very popular, have been used in spatial models forever, have been used by geoscientists. In fact, the particular form we have with a Matern covariance would be what I believe Kriege used back in the day. And they became much more popular for computer models in the late 80s and of course by machine learners in the 2000s. All right, so why? There's lots of ways to model data, and statisticians are very good at this, so why use this? Well, okay, let's suppose I have a computer model here, the black curve, and I've got 5 observations from it, which are the circles that you can see, hopefully. If you notice, this is a deterministic model. So when I plug in an x, I observe a z of x there. Okay, so if I were to estimate the model, if you will, estimate the parameters of the model, one of the convenient things of this model is that the predictions are linear in the data. So if you look at this y hat at some predicted x star, if suppose we had a zero mean, then what I would really have is something times a vector, if you will, times the vector of observations y. Important bits here, so we have R inverse, that's our estimated correlation matrix, and this vector R, small r, transposed. And that is an M vector. I have M observations. And that is a vector of correlations between the place where I'm making a prediction, or response where I'm making at X star, and all the other data points, right? So what we end up taking is a weighted average of the data, and the weights correspond, or the weights are determined by the correlation between the response at X star and the other data points. So close by points will have more influence, so will have higher weight, and far away points will have much smaller weight. And we can compute a predictive variance as well. But the neat feature in the deterministic setting is that the prediction error, if you will, or the predictive variance at the data points is going to be exactly 0. It should be in a deterministic sense. And as you move further away, you get this kind of football shape as I move from one data point to the next. And you can imagine that, what is that really saying? It's saying, well, points near where you actually have observations are going to have less, you have more information, you have less error than you do as you move further away from the data. So this is the sort of uncertainty that you would expect from a deterministic model and may want in this setting. So if you did straight regression, you'd end up with a typical tube, if you will, around the response surface, and that wouldn't represent the uncertainty that you would expect from a deterministic model. So GPs tend to do well for small to moderate sample sizes. In large dimensions, I'm going to say in higher dimensions, you have to fill up the space, and you're not going to get small sample sizes. And as I mentioned, there are some methods for dealing with that. But really, we're also looking at smoothly varying functions. That's a typical, at least in the typical formulation. Okay, so back to our case. And so we need an emulator that will adjust for essentially discontinuities, right? So the usual GP specification wants this smoothly varying sort of thing. And I've got a stationary covariance specification there. So it's going to be a bit of a problem when you have these, this is kind of a toy example of where you have regions of activity. We've got response surface on the top of these islands and 0 everywhere else. So the compass model is thought to be smoothly varying in the active regions, but of course, as I said, you don't get a response in some areas of the input space. And so the standard GP isn't going to, it's going to struggle at the very least with this sort of response surface. Okay. Actually, before I go on, I should have said at the start, if anybody has any questions, feel free to jump in. I probably won't notice any questions in the chat, so I don't have the chat box open. But if there are questions, please dive in and feel free to interrupt. Okay, so deep Gaussian processes. Okay, so they're probably, I mean, there's a deep something for any statistical model out there, it seems, these days. And really the idea is to fit more and more complicated response surfaces as a function of the inputs. There are two broad formulations for deep Gaussian processes, one by Damiano and Lawrence, and the other one by Dunlop et al. And this has made its way into the computer model world in recent years. So what we're going to do is adapt this method of Dunlop et al. To incorporate some prior information about the smoothness of the computer model, develop some theoretical result, and work out some of the variational inference for this. Now we have to do, one of the challenges with GPs, as I have up here, you have to compute the inverse of the correlation matrix, or for evaluating a likelihood, if we're doing MC or maximum likelihood, then we have to evaluate the Gaussian likelihood, and it's going to have the inverse of the correlation covariance matrix. And that's going to be, the size of the matrix will be m by m, where you have m data points. And we really don't want to be inverting a 2 million by 2 million matrix a whole bunch of times. Okay, so we move over to doing some variational inference. Now the adaptation that we make is fairly simple, but it actually helps a lot in some of the toy examples, and certainly helped with us with the compass example. But it also leads us to, this was part of our step towards understanding what these things are actually doing. And in particular, we looked at one by Dunlop et al. Okay, so let's take a look at the first formulation. So a deep Gaussian process with capital N hidden layers is defined by the composition of GPs. So at the first layer, if you will, so U1. Oh, by the way, this is a map from RD, so of a d-dimensional input to some other d prime dimensional space. And typically this is, not always, but this typically remains a d. So d1 prime is going to be a d-dimensional input as well. And all the subsequent ones will typically be also the dimension of the input, but it doesn't have to be. And in fact, there's interesting results, not theoretical, but interesting computational results, and where they actually do change the dimension of the input. Okay, so we've got these hidden layers. So the first one is a Gaussian process with, say, known covariance function. So it takes in the inputs x and with parameters theta 1. So we go to any other hidden layer. So let's suppose we go to the second hidden layer. So U2 would be conditional on U1. It's conditional, also a Gaussian process. But the parameters now are going to be U2 of x1, U2 of x2, all the way to U2 of xm. Okay, so what's really happening in this formulation is that the inputs, which were originally in the d-dimensional space, those are your, I'm going to call your native inputs. What's going to end up happening is that as you progressively move through the layers, you're going to get each hidden layer is going to be conditionally Gaussian based on the previous layer. And the previous layer is actually giving you the input locations to the next hidden layer. So the U1s are actually the hidden layers, or actually the locations, if you will, of the X's, but they're they're now used, but they're the locations of the data points, if you will, in the second layer, and so on. And the n+1th layer is actually our data layer in this formulation. So what's really happening here is that the inputs in your usual space are being moved around so that you can get closer and closer to a stationary Gaussian process. The design points are going to be whatever the U's are at the previous layer. So the final hidden layer is UN. And so this is a generalization of the non-stationary GP model by Schmidt and O'Hagan. So they had one hidden layer. So there was a U1, and then there was, if you view this from the ground up, we've got U1, and that's the first hidden layer, but there's no second or third hidden layer. They would have the data conditional on the U's would follow a Gaussian process, and really what they're doing is moving the points around in space with based on the that it's really just a prior on the locations of the input space. So the U1 is a prior on the input locations. And that actually, the Schmidt and O'Hagan approach is actually a variation of the Sampson-Guttorp specification of a Gaussian process. Okay, the second method, the one that we're going to really talk about here, is the Dunlop et al. Method. And here they also start with there's a hidden layer, so that's U1, and it's also conditionally Gaussian, so it looks the same. But as you go through, if you notice the U's themselves, so UN is a map from RD to R, to the real line. And on the right-hand side, I've changed things a little bit. So the kernel now is written as a function of X, and a function, the theta is just sitting there to tell us this is also a function of the U's at the previous layer. So those are the parameters. So what's happening here, as we start with this U1, we start with a d-dimensional space. U1 is literally a scalar, so it's R1, right? So now we have U1 being a Gaussian process in one dimension, and U2 will also be a Gaussian process. Conditional on U1 will be a Gaussian process in the first dimension, and so on. So what's really happening here is what's changing is the covariance as you move across the input space. So what the U's represent is a length scale function. Okay, so the length scale, this is still a function directly of the inputs, X, but the length scale is changing so that you can adapt for non-stationarity. So the correlation between X1 and X2 or the observations at X1 and X2, maybe some value. And if X3 is the same different distance from X1 as X2 was, so I want the correlation of observations between X1 and X3. In fact, it very well could be different, and the differences are taken into account by this length scale function. So this builds on the non-stationary modeling work of Paciorek and Shervish. This is the other CMU link to this talk. So there's Carrie Kaufman's work and Chris Paciorek and Mark Shervish's work. So what the deep Gaussian process does, this Dunlop et al. Method, is really just continuously apply on the hidden layers the Paciorek and Shervish method. So the final layer, the n+1th layer, the data layer, really aims to be a stationary covariance in the U's, the previous layers look to be stationary in the U's. So what you end up with is a non-stationary covariance function for the data. That's the aim, really. Okay, so what is that covariance function? So you could start with any stationary, in this case, isotropic covariance function. You don't have to be isotropic, but that's what we've used. And okay, the subsequent layers, you're like, oh my gosh, like if there's any grad students online, this is where they start checking their email. So don't do that. Okay, so what we want here is the correlation between an observation at X and an observation at X prime. And all the stuff before the correlation, before rho, is really, those are terms that are to make this a covariance function. So what we want here is this rho S bit, right? And the stuff that goes in it. So the important part is this Q. So rather than using the straight Euclidean distance or the square of the Euclidean distance, what we have here is we have these two matrices, sigma of un minus 1. So we're looking at the kernel at the nth hidden layer, conditional on the previous one. So the n minus 1th hidden layer. And we've got two matrices here. So we've got sigma for the first one and sigma for the second one. And we think of this as the average of those two. What are those things? So those things, those matrices are going to be actually diagonal matrices, and really it's just a constant times an identity matrix in this formulation, times some positive function. And that positive function, actually this should say un minus 1, by the way, in the power of the exponential. That positive function is going to use the u's at the previous hidden layer to adjust for how the covariance is actually changing, or the distance is changing between the observations. So this is kind of changing the distance, if you will, as we move across the input space. So it kind of allows the points to move and to move apart closer together, so that when you compute the correlation between observations at different points, just because x and x prime, as you move across with different x and x primes, if they're the same different distance, what you want is the correlation to somehow adjust as you move across the input space, if in fact you have a non-stationary model. All right, so again, what are the comments? The u's in this setting adjust for the correlation length scale as a function of the x and x prime. Now, there's this other bit here, right? So there's a choice of that positive function of the u's. So here we have an exponential of e to the alpha times un minus 1. There's the choice, and there's the choice of the parameters in there. Now, it turns out, if you really squint hard, what you'll see is that this parameter actually controls the smoothness as you move across the input space. Okay. So, and you can see this if you work out the differences here, that you know, what you really have is the average of the distances are changed by the average of these the e to the u's, e to the alpha u's at the different locations. Okay, so again, the alphas, the parameters, the u's are the thing that allow us to adjust parameters, but how smoothly that, the u's allow us to adjust the correlation as we move across the input space. So those are parameters to be estimated, but alpha allows us to tell how smoothly that those correlations change. Okay, so, all right, so big deal. All right, so here what I've done, each from left to right. So the left panel of plots are a realization of a 7-layer deep GP. So the final layer is your data layer. The first layer is the first hidden layer, and the second layer is the second hidden layer, conditional on the first, and so on. Now, so what we see with we have chosen f of u here to be 0.1 times u n minus 1. So the 0.1 is our alpha value for alpha. And if we look at the 4 realizations that we see on the left panel, they're all fairly smooth. In fact, a stationary GP would probably do a very good job. So we move across, we've got alpha is equal to 1 if we look at the middle panel. And it's a little bit rougher, if you will, in the hidden layers, but also a little bit bumpier as we go across. And as we let alpha increase to alpha is equal to 2, we see the final hidden layer is much bumpier, and also you can see a lot more evidence of non-stationarity in the response surface. So that alpha actually does something. And as you move alpha along in higher dimensions, you actually realize that, you know, if alpha is very large, you're going to need massive data sets to be able to detect that non-stationarity and actually estimate alpha well. Okay, so so this is kind of what it's doing, and we felt at this point, by looking at these things, you know, we should learn something about what the model is actually doing. All right, so one of the propositions that we can actually prove is that un minus 1 is constant only if and only if un, so if I have the n minus 1th hidden layer, if I go to the next hidden layer, it's constant if and only if un is actually a stationary GP. So it goes both ways, right? So if un is a constant, then un minus 1 is a constant, then un is conditional on un minus 1 is going to be a stationary GP, which gives you an idea of if it's necessary to do a deep GP at all, because what you would get as you're estimating those layers, you get something that is essentially flat, okay, as you move across. And you can think about why this would happen, right? If un-1 is constant, then we go back up to this formula here, then f of un-1 at x and f of un-1 at x prime, those are going to be the same value. So regardless of the distances between x and x prime, regardless of the locations of x and x prime, as long as their distance is the same, then the adjustment to the covariance will be identical for each points. Oops, jumped ahead. And there's a similar result for the space warping sort of things. In other words, if you're doing the space warping sort of approach, if you take 2 points in the original inputs and they don't change at the next input, or their distances don't change. In fact, if all the points, the distances between the points essentially remain constant, so the space warping is actually doing nothing, then that only happens if you're if you have a stationary GP. And there are, for one hidden layer, you can actually derive the equivalence between these two specifications, but beyond that, that is, I don't want to say not possible, but that's certainly not easily within reach. Okay, a few more things about DGPs. This is the formulation that we have. I've written it this way to say that the kernel is still a function directly of the inputs with parameters, but those parameters, as I said, are the U's at the previous stage. Again, we can view this. So the other thing is, when you read this literature, you know, where you're presented as, you know, here's the first hidden layer, here's the second hidden layer, and all the way down to the data layer. It is a bit, it's not backwards in any sense, but it's backwards for a statistician in the sense that what we do is we write down the data generating process, and then we'll put priors on parameters or hyperpriors and so on. And in fact, it works this way, right? So if you think of yourself at the final layers, you have y of x. Given the previous hidden layer, that'll be a GP, okay? And with this formulation. Now, the parameters themselves have a prior, right? So if there was only one hidden layer, right, then the prior on the parameters would be this U1 following this particular formulation of a GP, whatever you chose for K1 is your covariance function. Okay, so I would kind of go from the bottom up as opposed to from the top down. I wouldn't write down the first hidden layer naturally. What I would write down is what's the data generating mechanism, and then what are the priors on the parameters. And as I said, the parameters here are going to be U, alpha, variance components, and so on. All right, now, okay, so it's great. We have a model. And again, I want to get back to that compass thing eventually. We have inference that we have to do though, right? Because we have to estimate all the U's and all the statistical model parameters directly, which, you know, I think of sigma squared, alpha, and so on. Now, if you have a very complex function, you're going to need a lot of data. Now, in the compass example, we do. So the reason I'm mentioning that is that even in like 3 or 4 dimensions, if the function is really strange looking, and your goal is to be able to make predictions, and you know, if you have these discontinuities floating around, you're gonna need a lot of data to discover them, right? Like a lot of change point problems and so on. This is an issue. So MCMC quickly becomes unsuitable, right, to do direct sampling, right? And so what we did was variational approaches. There are other approaches you can take, but we decided to use a variational method instead. How am I doing for time here? Maybe I will skip. I'll just say that for variational inference, the idea is to choose some family of distributions for the unknowns at each layer, in this case, the U's, and whatever parameters we have to estimate, and try to estimate the closest Q, or the member of that family that is somehow closest to the true posterior distribution. And closest is measured by the Kullback-Leibler divergence between the simple model, in other words, the model with Q, and the actual posterior that's hard to evaluate. And we can't do this directly, and instead, as many of you know, you would use something called the evidence lower bound. Okay. The trick is actually, I mean, putting this aside, and you know, I'll leave a talk on variational inference aside. The key thing is being able to derive that for the particular setting that you're in, to actually derive an evidence lower bound. So the approach for inference we're going to use is something called doubly stochastic variational inference. It's a mouthful. But really, this stochasticity comes from a couple of places. One is that we're going to use inducing points. And you can think of those as pseudo observations rather than pseudo. Well, they're basically taking in all the information that we have in order for us to do quick prediction. So those are our inducing points, and they have to be estimated. In fact, they'll be optimized in this case. Oh, no, actually, we're going to estimate them, I think, in this talk. And the other thing is that we can't actually evaluate the full deep GP because we have 2 million data points, and that would require for each hidden layer the evaluation of a likelihood that has a 2 million by 2 million covariance matrix. So this is one of the reasons that MCMC is not going to be appropriate, and doing the full variational inference, using all the data at once is going to be not possible. So instead, we're going to use the mini batch sort of approach. So we have this has to do with our these are our two sources of uncertainty, which are going to come one because we're going to reduce everything using the inducing points. We're also going to subsample our data repeatedly in order to do our inference. And we also have to adapt our model to the evidence lower bound. Okay, so what are the key modifications that we're making here? Well, the model is different. We've included that alpha parameter, and I'll focus on that. There were some other modifications, small modifications that were made, but that's the important one. We have to adapt the variational inference accordingly, and the big deal here is, for those of you who want to do this, is to choose variational distributions that are somehow easy enough to sensible for the application you have, and somehow easy enough to do mathematics with. We can do that because we're choosing Gaussian distributions for the priors. All right, so there's the high level view of all this, and let's look at a toy example. So suppose I have this computer model. So I've got these 3 city blocks here, if you will, and the input space is from 0 to 1. And the city blocks looking down on 0 to 1 are those regions of activity that would kind of resemble the compass model. Now, the compass model isn't going to have nice little rectangles to live over, but nevertheless, it's what we have here. We're going to use 200 inducing points, and we're going to validate the model on a 70 by 70 grid in the unit square. Now, how we're going to measure the goodness, and this is often what's done, we'll use what we're calling what is often called the Nash-Sutcliffe efficiency, but it's something that resembles R squared, and what we're doing is taking the mean square prediction error divided by the unstandardized variance of the validation set. Okay, when we actually do that, so we turn the crank, we do our variational inference on our deep GP, and we get our thing that is like R squared. So when we actually do the variational inference on R squared, so in other words, we put a prior on R squared and do the inference, put a prior on it, put a variational distribution on it. The R squared is 0.92 with a coverage probability of 0.94. We leave alpha is equal to 1. We get about 90%. And this kind of ranges, the difference here is only about 4% of the reduction of the overall variability. And we usually get somewhere between 10 and, I'll say 0 and 10. So sometimes there isn't a lot. Now, if we just optimize alpha, we get pretty close, right? So in all cases, this is not true in all cases, but oftentimes then putting a prior on alpha and then finding an optimal value. So think of this, it's not exactly the same, but think of it as taking the MLE and using that only rather than putting a variational parameter on it. And we do a little bit better, but ultimately doing the variational inference allows us to take whatever uncertainty we have in alpha and bring it forward to our predictions and also our coverage probabilities. Okay. All right, so back to Compass, back to the computer model that we were really interested in the first place. All right, so we have a 12-dimensional input space, and the inputs include things like the common envelope ejection efficiency, the mass of the initially more massive star. So M1 is always the biggest of the two, M2 is always the smallest, how far are they apart, and so on. Okay. All right, and there are parameters that have to do with the merger itself. Right, so we've got about 2 million, and about a quarter of them actually give a binary black hole, observed binary black hole formation according to the model. All right, so I mean, I'll just note that there was a whole lot of time. So this is one of those cases where some sort of importance sampling or sequential design would have been really great in order to more efficiently sample that input space. All right, we kept about 1,000 aside. We kept 1,000 validation runs aside. 450 were active and 550 were inert. We could have kept a quarter, but really want to do well on those active parts. We fit a 3-layer deep GP with a mini batch size of 5,000, and we had 100 inducing points. We went up to 1,000 inducing points and didn't do a whole lot better. So we actually did a little bit of training on that, or investigation on that. And the priors on all parameters were Gaussian, in particular for alpha. We had this normal 4, 1.5. Now, why 4? One of the things we noticed while we were doing to build some intuition on alpha, and in particular in these examples like this, was we found that that in general, the more complex the response surface, and by complex I mean kind of really changes in stationarity, if you will. The larger alpha had to be to accompany that. Now, in high dimensions, that's not always going to be true, and because of the way the GPs tend to behave in high dimensions, that small changes in roughness parameters can result in very complex response surfaces. Yep.
Quick reminder: 10 minutes left.
Yep, absolutely. I'm going to finish this example and wrap up. I think I'm on time, but thank you. Okay, so this is the case that we had, and prediction, a lot of it was their gain. And let me just tell you about this. So for our validation set, so we turned the crank here and on the variational inference in this case. And all right, so let's take a look at the left-hand plot. We've got the true chirp mass, in other words, what the simulator actually spit out in our validation set. And on the y-axis, we have the estimated chirp mass. Now, if you notice on the left-hand side, we've got a whack of zeros, a lot of observations of zeros, and that has to do with our 550 inert observations. And much of the time, although it's hard to see here, you can the observations are 0 or close to 0, or the predictions are 0 or close to 0. But when you don't predict, then the errors can get large-ish, but they're not too bad. Most of them, occasionally. What this is really doing, if you look at the largest error there at 0, what it's really doing is saying, oh, if you think back to this previous example, it's really saying that the observation is at the top of one of those buildings. So it's really just predicting the wrong thing entirely. But most of it's done pretty well. If you look at the active data points, which you see on the y is equal to x line there, we're doing a pretty good job. It's nicely, tightly, it's nice fit around the x is equal to y line. The Nash cycle efficiency, or this kind of pseudo R squared, was 0.96, and our coverage probability was about 0.92, or 92% in this case. All right, so for the most part, it's doing pretty well, right? So you know, the prediction errors are the absolute prediction errors are relatively small. Now, there was a paper from our group as well by Yu-Lao Lin, and that appeared in the Annals of Applied Statistics using the same data. And that work included a local classifier to say it's in the active region or is it not in the active region, and a local GP. The challenge with that method, so that method did pretty well when the classifier did the right thing, if you will, but unfortunately it misclassified about 40% of the training data. So this deep GP method did quite a bit better at prediction, but also in uncertainty quantification, which matters to the astronomers. Okay, so I'll recap here. I think I'm on time. So we've adapted the deep GP to include some prior information on the smoothness. This actually helps us quite a bit. I didn't show all the simulation studies for that, but getting that wrong can mess around with things, and you need a lot of data to overcome that. we developed some theory to explore the model performance, at least understand what it's doing, and certainly come up with kind of a rule by how deep you actually have to go, because you're looking to essentially achieve stationarity, and that constant trying to go where one layer is essentially constant really helps a great deal. We applied this to emulate this compass model. Now our next steps are to use it, and we started this to use the distribution of observations and the emulator. So to actually use the physical observations and the emulator to constrain the distributions of inputs. So, for instance, as an example, if you wanted to say, well, what is the distribution of the masses of primary stars? There's a prior on that, but can you constrain that from data? And we started developing the methodology for that. And it's not finished now, so I don't have any plots to show you for that. But anyway, that's where we're headed. I think I will stop there and just say thank you for indulging me.
Thanks so much for an excellent talk.